Recorded and rolling. It is Friday, November 8th. Here's top scientist for the last quiz. You guys can turn in a couple days back. Circular motion and gravitation orbit. So awesome job if your name is on that list. All right, so I have not handed back any quizzes yet. I do have three different classes, so three different types of quizzes, but I don't have all the quizzes from, well, any of the classes. So gonna wait a few more days to get some of those in before I hand them back. Now, after I give them all back, then if you guys want to do corrections, then you'll be able to do that. But in time. All right. So, guys, yesterday, you guys remember the pendulum speed lab? You guys calculated what's the speed of the pendulum using conservation of energy. You guys measured it empirically with the speed gate. A lot of you guys turned that in already. Guys, if you didn't turn that in yesterday, then just turn it in today, and I'll give you guys some points in the gradebook for that. You guys have your energy tables out ready to go because we're going to finish these today. All right. Then homework. So on Google Classroom, I posted a link to Mark Rober's Pinewood Derby car video. You guys remember Pinewood Derby car? So how do you create the optimal car to win the race? And a lot of this thought process is exactly what we're doing in class this week. It goes through conservation of energy. It's really good encapsulation of good application of this stuff. All right, so of course today's Friday. I'm not going to see you guys on Monday because of Veterans Day. I'm also not going to see you guys on Tuesday because of FCLE. I think that stands for Florida Civics Literacy Exam. Is that right? Thank you. And so here's what's going on Tuesday. Or here are my class relocations. So you guys are going to go to Smith and Ford 225 rather than this class, unless of course you're taking the exam. If you're taking the exam, then you should see that in an Excel file I posted to Google Classroom. It says exactly where each student is taking that exam on Tuesday. Okay. And if you're not taking the exam, then there's a good chance that some of your classes, including this class, are going to be relocated. So there's another Excel file that does all the relocations. It's all posted to Google Classroom. I think it was there a couple days ago. Okay. So all that information is out there. Okay. So after today, the next real day of school is going to be on Wednesday. All right. So you guys ready to go? Ready to go? All right. So, here's our checklist right here of forms of mechanical energy. So the ones we care about for this table. Looks like the last one we did was just block, spring, earth. So let's recap that one real fast just to think about how this works. So I push this mass into the spring, earth, let it go, flies around the loop. Okay. So the energy was stored in the spring. So in terms of energy, that's 1/2 kx squared. Right? If you know k, the stiffness of the spring, and you know x, how much you squash the spring, you can calculate how many joules. Suppose it's like 100 joules. Right? Then by the time it gets to point B, that energy went to two different places. You had to lift it against gravity, call it mgh, and whatever's left over went into its motion. And the energy term for that is kinetic energy 1/2 mv squared. So this turned into this and this. Boom, boom, boom. Okay. Right. Guys, suppose this was 100 joules. Do you guys see that? 100 joules? Right. Suppose it took 20 joules to lift it. How many joules are left over for motion? 80, right? So you go 100 equals, throw a little equal sign here, 100 equals 20 plus 80. That can be true, right? Then, yeah, I know, mind blowing, isn't it? Then, if I gave you the mass, could you plug in the mass right here and then solve for V if you want to, solve for the speed? So you could do that, right? Right? That's a little recap. All right, let's do, actually, you know what? Let's do this one. I'm going to solve one of these in terms of variables with you guys. All right, you guys ready to stretch your imagination a little bit? Right, you guys ready for this? All right, so you guys got some paper out, ready to go? Let's do, I'll start from the beginning. Sum of energy initial equals sum of energy final. Or I could do point A to point B. Let's call it point A and point B so it matches the table. Right. Right. Then it was all 1/2 kx squared in the spring to start with. Right. Then by the time it gets to point B, well, it had to be mgh, but also 1/2 mv squared. So both of those. Right. Let's say we're solving for that v. Right. No, I changed my mind. I'm gonna throw some numbers in here for you guys. Let's throw some numbers. Let's say if x is let me think what do I do here. Hold on, let me make something up. Let's go 1 meter. I know this is crazy, but I'll just do it. 1 meter. Let's call k like 200 newtons per meter. Right. Let's say the mass is like 0.1 kilograms. let's have G be 10 meters per second squared. Let's have the height be like 1 meter. And then, okay, the mass shows up here again at 0.1 kilograms. And we can solve for the speed. Okay, I just put up some numbers on the fly. I hope this works out. We're gonna see. We're gonna find out. All right, guys. Okay. So somebody tell me, guys, how many joules were in that system to start with? Times a half is 100. Yeah, got 100 joules right here. 100 joules of energy. Right. How many joules of energy went into? Wow. Can I change this to 1 kilogram? Is that okay? Let me change this to 1 kilogram. Got 1 kilogram. Okay. Guys, how many joules went into lifting it against gravity? What's 1 times 10 times 1? 10, that's right. 10 joules. Okay. So how many joules would be left over for kinetic energy?
1 squared.
Yeah, 1/2 v squared. And how many joules is that?
90.
90. That's right. I got 90 joules equals 1/2 times 1 times v squared. Okay. So can I say 180? Now this would be actually joules per kilogram at this point because I got kilograms right here.
Where'd you get 180?
Oh yeah, guys, where did I get 180?
Never mind.
Okay, cross multiply the 2, right? V squared. Okay, and then so v is, what would the speed be? So you can solve for the speed like that, right? Is that? Okay. So here, let's do this. In this box, here, let's say if K equals 200 Newton per meter, M equals 1 kilogram, X compression equals 1 meter, G equals 10 meters per second squared, and H equals also 1 meter. All right, so crazy numbers. Then here's your answer. The speed at the top is 13.4 meters per second. Okay, that's what we just did. Right. Okay. Huh? Oh, that right. Yeah. All right.
Can you do the solve for B?
Yeah. Okay. So all I did was just wrote down exactly.
Is that mu?
So this is K is 200 Newton per meter.
Oh,
Right. Kind of like your guys' spring scale is probably pretty close to that. Mass is 1 kilogram. The compression distance, I put 1 meter. Gravity field 10 meters per second squared. Let's say this height change here is also 1 meter. Right. If you had that exact set of numbers, then this block would be moving at exactly 13.4 meters per second at the top.
B.
All right, guys ready for bungee jumping? It's bungee jumping time. A bungee jumper dives off a platform and barely touches the ground. The cord retracts. Okay, so I'm gonna put the jumper here. I'm gonna put the earth because there's a height change. Right, but guys, ultimately the energy goes into the what?
Jumper.
The bungee cord. Bungee cord. All right, there you go. Bungee cord right there. Okay. Right. At point A, where was all the energy?
Jumper.
Yeah, MGH, right?
Oh.
MGH. Okay.
Yeah.
You guys tell me what you want to do. Do you guys see the word dives there?
Yeah.
I'll leave it up to you guys. Do you want this guy to be just stepping off and falling from rest? Or do you guys want this guy to do a running jump? Like, yeah, wee, and jump off. What do you guys feel like doing?
Step off.
Huh?
Step off.
Just step off? Okay. If he just steps off, then that's all the energy, isn't it? Okay. So I'm gonna cross out the word dives off and it'll just say steps off. Okay. All right. So he's falling. He's probably in free fall for a little bit, but not forever, because then that bungee cord starts to stretch. By the time he gets to point B, he can reach out and go, just touch the sidewalk, and it retracts. Swing, pulls him back up. Okay. So at point B, all the energy is in the what?
Person.
the bungee cord, right? And which expression here do you think could express the bungee cord? Aha, spring potential. The bungee cord is basically a spring, isn't it? Yeah, we'll call it 1/2 kx squared. Right? Can I just say equals right there? Right. All right, let's do the same thing we did before. I'm just going to make up some numbers. So say we got oh, but before I do that, the actual question here is what's the speed of point B? Guys, what is the speed of point B? 0 meters per second. Okay. I still want to make up some numbers, but we're not going to solve for the speed because obviously that's just 0. Okay. Maybe I'll solve for how much does the bungee cord have to stretch, right? So suppose that I give this guy a mass of 50 kilograms. I put him in a gravity field of like 10 meters per second squared. Let's say the height of the cliff is like 20 meters. Let's say the spring constant for the bungee cord could be like 1,000 Newton per meter. I don't know if that's even enough, but we'll see. But we're going to find out how much does it stretch. X equals what? That's the question. Right, that's the actual question I have for you guys. How much does the bungee cord have to stretch? Okay. Let's do that. So we just said MGH turns into 1/2 kx squared. That's from conservation of energy. Right? Let's just pop the numbers in. Got a 50 kilogram guy and earth gravity. And the height of the cliff is 20 meters. The spring constant is 1,000 Newton per meter. How much is the cord going to stretch? So you can reach down and just touch the sidewalk. All right. All right. Guys, how much energy is in the system?
10,000.
That's right, 10,000 joules. 10,000 joules right there. Half 1,000, that's like 500. Can you guys solve for X? Okay, you guys solve it, I'll solve it. Let's see if we get the same number. Get 20, and then after you get 20, you have to take the
Oh, square.
right.
4.27.
Yeah. Yeah, I'm getting the same thing, like 4.47 meters. Okay, I think that worked out. 4.47 meters. Right. So I have a 20-meter tall cliff, and this thing has to stretch about 4.5 meters. So I think the unstretched length of my bungee cord is probably about 15 meters, right? It's about 15 meters long, and it stretches an additional almost 5 meters. You can reach down, point, touch the sidewalk. I guess that. All right. Ooh, I got a couple of Atwoods. Atwoods time. No, you guys have seen Atwoods before. You guys did a lab on Atwoods, and this was one half of the lab, and this was another half of the lab. Now, back in the day, what I had you guys solve for was what was the acceleration based on the masses. And once you know the acceleration, what you could do is you could flip back to kinematic motion, and you could say, oh, I just found the acceleration. So I could say, how far does it fall after how much time? How fast is it moving after how much time? Or how fast is it moving after some falling distance? You could have done it. That's the old way to, you could have done that like 3 weeks ago. Okay. But now there's a new way of thinking about it, which is going to give you the same answer anyway. Kind of like, you guys remember the car braking to stop? We solved it the old way, and the new way we got the exact same braking distance. Okay. So same idea here, just with Atwoods. I got some Atwood posters too, but we'll look at those in a minute. Okay. So first one, now this is a single elevator Atwood, modified Atwood, and there's no friction. There's no friction on the surface. Okay. I'm going to include M1 and M2 in the system.
Sure.
But also, guys, the fact that there's a height change, I also need to include the Earth. Right? Earth. Okay. All right. What kind of energy at point A?
Potential.
Potential energy. Yeah, M2GH. the fact that this block hanging over the edge is about to fall. That's like supplying the energy. By the time it gets down to point B, which is pretty much ground level, what type of energy? Kinetic, 1/2 mv squared for that block 2, but also it's pulling along what? Block 1? That's 1/2 mv squared on block 1. Would that be true too? All right, let's get some blocks going. I'm going to call M1 equal to, let's say 10 kilograms. Let's call M2 1 kilogram. That could work, right? This could be 10 kilograms. This could be 1 kilogram. Let's call gravity field 10 meters per second squared. Let's call this height change like 1 meter. Okay. Therefore, the speed is going to be, we're about to get an answer right here. Okay, you guys ready to solve that? Got to throw an equal sign there. You guys ready? All right, so paper time. So Atwood, sum of energy at point A equals sum of energy at point B. At point A, it was all M2GH. At point B, well, it doesn't have any height anymore, so there's no more potential energy. But both of those blocks are in motion, in fact, with the same speed. So I got a 1/2 mv squared for block 1 plus a 1/2 mv squared for block 2. And this speed is this speed. Because they're tied together, they're both moving the same. I mean, one's down, one's to the side, it's different direction, but that doesn't matter. Right? Because all this energy stuff is just a scalar quantity. So it doesn't matter direction motion, it's just moving so fast. Okay? You guys get that set up? Okay. Get ready to pop in some numbers. So I said M2, let's call this guy 1 kilogram. Put in Earth gravity of 10 meters per second squared. Let's give it a table height of 1 meter. And then now M1 I made really massive. I made this guy 10 kilograms. Some speed squared plus 1/2. And this guy's, M2 is 1 kilogram again. Moving at some speed squared. Guess how many joules of energy were in the system?
10.
That's right, 10 joules. And here, well, half of 10, I'll call it 5. There's a kilograms attached to that. Got a v squared plus, okay, got a half here, and some of the kilograms, and a v squared. Okay. Hey, guys, what is 5v squared plus a half v squared?
5.5.
That's right, 5.5 v squared. 10 joules equals, I got 5.5. I still got a kilograms, and then v squared. Okay. Could you guys finish that off with algebra? Oh yeah. Here, let's see. I haven't solved it yet. You guys think you beat me. 10 divided by 5.5. Okay. So v squared equals 10 divided by 5.5. And look at 1.818. Now the joules over kilograms is meters squared per second squared. And guys, what's the very last step?
Oh, square.
Square root. Okay. Let me show you guys a fancy way to take a square root. Okay. Do you guys see this caret key right here to the top left of the 7 to the power? Okay. Guys, do you have on your screen 1.1818181818? You guys got that? And you got that by 10 divided by 5.5, right? Okay. Hit that caret key. It says answer to the power of. Okay. Who knows? How do you take a square root with a power? The power of what? Not 2.
3.
What's 1 over 2?
Oh.
Power 0.5. That's a fancy way to take a square root. Okay? Right. There you go. 1.35, I'll call it, meters per second.
Why would you round up?
1.348. Like it's like 83% of the way to.
Square root of. Oh, because you did 1.818.
Yeah, just took the square root of the answer. All right, so that's the answer right here. So given these exact values, the speed would be 1.35 meters per second. No, you can keep your work with notes.
Oh.
All right. All right. Next one. Hey, look, it's the classic double elevator at Wood. Again, there's no frictional loss. Don't worry about anything like that. Okay. I'm gonna have same objects, M1, M2, and the Earth. Okay. You know what? Let's use the same values as before. Yeah, that'll be fun. Let's just copy paste these values right here. I'll just write same values. Okay. So, guys, what's the supply of energy?
M2GH.
Yeah, M2GH. Right. So the large mass is going to fall down. So then equals. Now, guys, that energy is going to go 3 different places. Everybody following this? 3 different places?
What?
What's one place it goes?
No.
Does some work to
Kinetic energy.
kinetic? Guys, at the end of this motion, the blocks are both in motion, aren't they? So I got some 1/2 m1v squared, plus I also have some 1/2 m2v squared. Where else the energy go? Potential energy of block 1? Yeah. M1GH. And then plus those guys. Right. There you go. So the large block, which is M2 falling, does 3 things. It lifts the small block, give it some M1GH, and also puts both of the blocks in motion.
If the potential energy is for block M1, why'd you put it for block M2?
Okay, so block 2 is falling down, so it's like supplying the energy.
Yeah.
It has to lift block 1. So over here, it's like here's the supply of energy. Here's one of the demands for energy, right? Has to lift block 1.
Yeah.
And it's the same height change on both of them. Right? One goes down, one goes up.
Yeah.
All right. So let's try this. Got sum of energy at point A equals sum of energy at point B. Right? At point A, it was all M2GH. At point B, had to lift the small block plus 1/2 mv squared plus 1/2 mv squared. Okay. 1, 2. Okay. That's a setup, right? Okay. Now let's use the same values for this one that we did on the previous one, and we're solving for V. You guys ready to solve for V right here? All right, let's suppose M2. Oh, actually, whoops. I have to swap M1 and M2. Is that okay if I swap M1 and M2? To put the heavy one on top. I'm going to make this guy 10 kilograms. Put 10 kilograms right here. I got 10 meters per second squared. Let's do a height change of 1 meter. Mass 1, I'm going to make just 1 kilogram. Little itty bitty guy. 10 meters per second squared here. 1 meter raised here. 1/2. Got 1 kg here. V I'm solving for squared here, plus 1/2 10 kg here. Times V I'm solving for again, squared here.
Yeah.
All right. Okay. How many joules of energy are in this system? How many joules? 100. We got ourselves 100 joules. How many joules went into lifting the small block? 10 joules. Right? Does that mean there's 90 joules left over for these guys?
Yes.
I think so. I got 1/2 times 1 plus 1/2 times 10. Guys, half of 10, that's like 5, right? Half of 1 is like 0.5. Could this be 5.5? I said say plus 5.5. I got a kilograms on there. And that's times V squared. All right, so subtract that over. Got 90 joules. Goes to 5.5 kg. And then V squared. Okay. Did you guys finish the algebra? Okay. Divide over 5.5. And after you do that, the square root. So the speed is say what is that right there?
90. Four point.
Aha. Yeah. I mean, same thing. So say V equals, it's like 4.05 about meters per second. There you go. It's how fast it go. Okay. Again, the old way you could have done it is you could have solved for acceleration first and then gone kinematic. You would still get the same answer. The new way, the way we just did here, notice it all fits on one page of paper, so you can probably solve it faster this way. If you ever see what's the speed after moving some distance, you can probably solve it fast with conservation of energy. Notice also we never even solved for the acceleration. We never even found out what the acceleration was. That's interesting too. Right. One thing to know. All right. So you guys get so far. Get so far. Right. Oh, and I said I was going to show you the posters. Let me dig up the poster. Here we go. Here we go. Right. There we go. Here's hey, that's what we just did. Look at that. The large block falling does three things. It lifts the small block, and it gives each block a speed. So I count that for kinetic energy. Boom, boom, boom. Right. I did have a. Well, this wasn't exactly what you're looking at, but it's kind of similar. Okay. So here's a large block falling, supply of energy in green. I did subtract off work done by friction, so it's a little tricky. Okay. If there's friction, and it lifts a small block and gives each of these three blocks of speed. A little bit different. Okay. All right, guys, ready for? Oh, it's springtime! Springtime. A spring fires a ball vertically to its maximum height. What objects do you think in the system?
The spring ball.
The spring, the ball,
and Earth.
And the Earth. Oh yeah. All right, that's going to create a closed system. What kind of energy at point A?
At point A.
Do all of these have Earth?
Potential.
Yeah, spring potential.
AX squared.
Yeah. A lot of these do. Whenever there's a gravity field and a height change, yeah, you're gonna have the Earth. All right, so that's that is most of these, isn't it? Actually, that's a good question. Do they all? Which ones? Earth. Okay, I guess the car didn't have the Earth. Okay. Okay. Right. That had the Earth. That had the Earth. Yeah, most of these do. I guess the asteroids won't. But yeah, most of these do. Yes, you're right. This would be 1/2 kx squared. That's right. The energy was in the spring. And then when the ball goes to its maximum height, where'd all the energy go? Into the
spring ball. Earth.
Let's call it MGH.
That's what I'm looking.
Yeah. I say equals. That's what you guys have, right? Right. Guys, what is the speed at point B? That's a maximum height.
0.
Aha, 0 meters per second. Okay, 0 meters per second. Okay. But you know what? I think we have a little extra time anyway, so I want to solve for something different. We'll just solve this on a separate page of paper. So, suppose K equals, let's go 200 Newton per meter. Let's say X is like 0.1 meters. Let's have mass be 1 kilogram. Gravity field is like 10 meters per second squared. Okay, so I'll give you all these values, call it given. And I want to know what is the maximum height equal to. Okay, right, you guys get that? Okay, let's solve it. All right, you guys solve it. I'll solve it. Let's see if we get the same thing. All right, I got the answer.
Wait, I'm still doing it.
Somebody tell me, what is the maximum height equal to?
Wait, I'm still doing it. 10 equals 10, 1.
Huh?
Square root 1. Cause it would be 10 divided by 10.
Guys, what's
Oh, I have to square that.
okay, right. How high?
0.0. Is it 0.1?
Ah, 0.1 meters. Isn't that like this distance right here? 10 centimeters? I think that's 10 centimeters, right? Is he 10 centimeters? Equals 10 centimeters. Right. That's really a better question than what's the speed at the top, which is obviously 0. Right? Yeah, better questions. How high does it go? It's 10 centimeters. All right. Next one. The ball falls from some height and squashes the spring. Gonna be ball, spring, earth. Yeah, ball, spring, earth again. System. Okay. What kind of energy at point A? mgh. What kind of energy at point B? Aha, 1/2 kx squared.
So
Let's
just
see.
the other one's backward.
It is. Aha, it is it backwards. Okay. What's the speed at point B? 0. Guys, good so far. Okay, so we've done 10 of the 12 examples. Okay.
Can you have a second box on the MG? What's that little
Oh, subscript A.
Why is that?
carry?
Oh,
A.
A. Yeah, because it's height A. It's height A. That's what that is. Right? Height A. All right. And actually, this one back here, I could have called that height B to match my picture here is height B, right? All right. So we've done 10 of the 12 stories so far, and they've all come out of these 4 gold boxes. And so out of all 10 examples you've done so far, they've all been these gold boxes. Now I got 2 questions left. And these last 2 questions, well, each one of these is going to involve one of these green boxes here. Okay. So these last 2 are a little bit challenge questions. You guys see a ball rolling down an incline? Ball rolling downhill? I'm gonna include the ball, what do you think else?
Incline.
The earth. Yep, there you go. That's it. The ball, the earth, and the incline. Or I said hill, so all right, hill. The ball, the earth, and the hill. Right. Now that's a little bit different than if you flip back the other day. Do you guys remember the kid in the sled in the earth and he slide down? You guys remember that? Right. Now, back this one we're about to do is different than the one the other day, although at a glance it looks similar. So what's the difference? The other day, there was a friction force that was making kid want to slow down. He wouldn't be going as fast as he would be if there was no friction, right? And we treated this as an open system. The kid had MGH. The friction force was taking work out of the system, so minus force times distance. And he was left off with some 1/2 mv squared at the end. Okay. Now the ball running down the hill, there is also a friction force from the hill, but it's not doing negative work on the ball. Instead, it's just inducing a torque. It's causing it to roll.
Is it?
Okay.
1/2 I. What is it? Sigma?
Omega.
Omega.
Oh, stop.
That's it. That's right. It's 1/2 I omega squared. That's right. That's right. Yeah. So, guys, this is a future topic we haven't talked about yet, but what would induce rolling? It's called a torque. Right? So there's no energy loss here. So this can actually be a closed system. Okay. So at the top, guys, what kind of energy at the top? MGH. What do you think of point B? What should I write for point B?
1/2 I omega squared.
True. 1/2 I omega squared. Now, if that's all you write, that's just the ball rotating itself. Guys, is the ball also in motion? Like in the lane?
So 1/2 omega squared.
Yeah, it has both of these. It has that and that. Both of those are true. Okay. All right. Guys good? All right. Now, this one here. that's as much as I'm gonna do with you guys on this one. But you could solve for how fast is the ball going. And I do have posters for that. Again, this comes from the future. We're from the future, Marty. It's right here. You have a ball rolling down an incline. Now, different kinds of balls are going to roll differently. Here I have a spherical shell. That's what a basketball is, basically a spherical shell, right? Right. If it was a bowling ball, which is solid, the answer would be a little different. If it's a solid cylinder, like if this guy's rolling down the hill, a solid cylinder, the answer again would be a little different than this answer. But here's a basketball. It turns out it's this right here. Right. Hey, does that look kind of like square root 2GH? Except instead of a 2, it's something that's smaller than 2. 6 is like, what is that, like 1.2, I think? Right. Right. Because some energy goes into making it rotate. So it's not going as fast as it would if it was like an air hockey puck sliding down frictional surface. Like that. All right. So just want you guys to see that that's there. Guys, this I, what this I is called rotational inertia. So if I'm trying to roll the cylinder, or if I'm trying to roll a basketball, or if I'm trying to roll a bowling ball, all those feel different. Even if they had similar masses, the fact that mass is distributed differently give you different I values. So actually I have this poster right here. Here's rotational inertia table. Here's what I is for each of these objects. So what kind of ball is rolling down? Well, if it's a basketball, I'll call it 2/3 mr squared. If it's a bowling ball, call it 2/5 mr squared. Okay. All right. So I just want you guys to see the big picture of like what the next steps kind of would be. Okay. All right. You guys ready for the last one? All right. 2 asteroids. Did you guys say each asteroid? All right. So we got 2 objects. Asteroid there, asteroid there. They're both in the system. Let's say they're in deep space and they somehow start from rest, but they're going to gravitationally attract towards each other.
Yeah.
Okay. Okay. Now for this one, this is a challenge question because they have potential energy, but you cannot say MGH because this lowercase g is always changing. So what do you think I'm going to say instead of MGH?
Negative GM.
Ah, negative GMM on R. That's all right. That's all right. So say negative GMM over, and they start off at radius A away from each other. Okay. Start with that. Okay. Then when it gets to point B, ooh, they're still separated, but not as far anymore. So that's negative GMM on RB. And they're also in motion, aren't they? Like speeding up, right? In fact, this is one of the rare times in this class that is not constant acceleration. So the only way to solve this is with this exactly.
Are they equal the cosine on
Yeah. So you can say equals, but I need to add more to this. I say 1/2 mv squared for one asteroid plus another 1/2 mv squared for the other asteroid. Okay. If you ever have 2 asteroids, if you ever have that exact scenario, you want to know how fast are the asteroids moving after some distance move? Right. So you're solving for this v right here. The distance move could be, well, the difference between RA and RB, right? And this is kind of the only way to solve this. Like before I said, well, if you have an Atwood, now you have multiple ways to solve it. If you have a car braking to stop, now you have multiple ways to solve it. The asteroids, this is kind of the only way to solve it. All right? You guys get that? Okay. And here, maybe see if I solved it before. See if I find that. Oh, here's by the way, here's the ball rolling down the hill. Don't worry about the details necessarily, but that's solved in terms of variables. Where's the asteroid? Here's the asteroids. Here's the asteroids. Right. So I got conservation of energy. Right. That potential in terms of potential plus kinetic. I gave them the same mass. If you do the math, this ends up being the speed at point B. Okay, this ends up being that. Okay. Now for you guys in your table, all I'm really looking for is just exactly what we did right there. Okay, are you guys good? All right, and that is going to be a wrap on that table. As long as you have everything we did in class filled out, go ahead, turn that table into the grade tray, and I will give you guys some points.